तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello, this is an introductory course on circuits and systems or networks and systems suitable for an undergraduate student majoring in electrical engineering with either the power or communication option. In this course, we will study the dynamic behavior of systems and networks. You will be exposed to a variety of tools and techniques which are used to study the behavior of the systems with the dynamic inputs, so that you can gain an appreciation of what particular technique to choose under a given situation. When talking about systems, we should also talk about signals. The input variables to a system, the response variables that we are looking for, and the various intermediate variables which occur at different points in the system are all collectively called signals, and this is a term which we will use to describe these variables associated with any system. Later on we will say that a network is a special kind of system, and the voltage and current variables associated with a circuit or a network therefore are also called signals in the particular context of an electrical network. These signals are usually functions of time. A study of the characteristics of the signals and their analysis therefore is an integral component of our course. As a matter of fact, it is the interplay between the signals and systems that will be the main theme and focus of our course. Among the topics which we will study are Fourier methods, Fourier transform, Laplace transform method, network functions, network theorems, Z transform methods, and state variable techniques. These will be the various topics that will be broadly covered under this course. We shall, for the most part, confine ourselves largely to the discussion of linear time invariant systems. The meaning of these two adjectives, linear and time invariant, will become clear as we go along. Suffice it to say that they form a fairly large class of useful systems. So at the end of this course, you will have with you a toolkit of available techniques, so that you can choose one of these techniques for the solution of the dynamic behavior of a network and system belonging to this very large class of linear time invariant systems. Before we proceed further to discuss the meaning of a system, let me first talk about the various textbooks and reference books that you may like to refer to during your study of the material under this course. You may use these books to have some of your doubts clarified, to deepen your understanding of a particular topic, maybe to get additional information related to some of the topics that are discussed here. But most importantly, you should use these books for working out the various problems and answering the various questions that are given as exercises in these books. Particularly for a subject with an analytic orientation like networks and systems, it is very important that you should work out a large number of these quantitative problems and answer these various questions. It is only through such exercises that you can form your understanding of the subject, make your grip of the various techniques stronger. And another important aspect with this is that, like in any other discipline, in networks and systems also, there will be always a number of approaches to solve a particular problem. Only through working out these various exercises you will be having the ability to choose the most direct method of attack for a given problem. You will have the necessary expertise to gain the insight so that you can select the most appropriate method of attack for the solution of a problem, and not only that, to carry out the solution correctly and in quick time. So I would once again emphasize the importance of working out a variety of problems, and you can use some of the textbooks which I am going to mention right now as a source material for these problems. Now, the particular textbooks that I would like to recommend are Haight and Kemmerly, Engineering Circuit Analysis, Van Valkenburg, Network Analysis. These two are very popular books in this field. Oppenheim, Wilsky and Young, Signals and Systems is very comprehensive. It gives a very comprehensive coverage of the topics that are covered in this course, plus some additional topics, and this also contains a wealth of problems as exercises. In addition to these three books, you have a book by Chung titled Analysis of Linear Systems, Liu and Liu, Linear System Analysis, and a sixth book by Athre, Network Theory and Filter Design. It contains discussion of some of the topics that we are going to cover in this course, like state variable methods and so on, which are not perhaps found in some of the other books. By way of background, I expect of you to follow this course. Let me mention that I expect the students to have a background on the following topics. I would assume that you have had a basic course in electrical circuit analysis, which includes the discussion of the properties of various circuit elements, DC and AC circuit analysis, AC circuit analysis under steady state sinusoidal conditions, and an idea of elementary transients, the time constants in RC circuit, RL circuit, and so on, and setting up the differential equations pertaining to simple circuits. This is a background in electrical engineering that one would assume. As far as mathematics is concerned, you should be familiar with elements of differential and integral calculus, solution of simple linear differential equations, ordinary differential equations with constant coefficients. You should also have an idea of matrices and determinants, solution of linear algebraic equations, and then elements of complex variable theory is also expected of you to follow this course. So this is the background what one would expect you to have to follow this course. Now let us discuss what a system means. All of us intuitively have an idea of what a system is constituted of through its usage in everyday terminology. We may formally say a system is a collection of components put together to serve a particular purpose. These components are system components, as they are called, are unified through some kind of interdependence among them. They react with each other so that the whole system functions as a whole to serve a particular purpose. We may think of a power system, the national educational system, hospital systems, railway systems, transportation systems, and so on and so forth. Many of these systems also have as an integral component the interaction of people, for example in socio-economic systems, All these are constituents of systems. Now therefore a system is a collection of objects united through some form of interdependence among the various components, or subsystems as you may call. Now the variables that describe the status of these various components in a system may be quite diverse depending upon the nature of the component, the nature of the system, and so on and so forth. For example, if you are talking about an electromechanical system, you may have the electrical variables, voltage and currents associated with the electrical components, and mechanical variables like force and velocity, which describe the status of a mechanical component at a particular point in the system, at a particular point in the system. Therefore system is an omnibus type of concept which includes a whole variety of situations that one comes across. Now what about a network? Literally speaking, a network is a structure which resembles a kind of net, but in our particular context we use a network, the term network, to describe a system in which all the components are of a related kind. That means the variables which are of importance in the system are all of the same kind. So in a particular electrical network, for example, is a special kind of a system in which the variables are voltage and currents most often. That is, these are the two variables which are of interest to us in an electrical network. Similarly, we can have a network representing a mechanical system which we will call a mechanical network, in which the variables may be velocities and then forces and so on and so forth. So we can think of a network as a special kind of a system. An electrical network in particular is what constitutes the focus of our discussion here. Now in analyzing these systems and networks, the first step usually is to model the system in terms of idealized components put together in a particular fashion. This evolution of the model is done with the two conflicting requirements in our mind. What are the two conflicting requirements? First of all, we should like to have the model as realistic as possible so that it simulates the real system. In other words, we should like to make the model as complex as possible so that we lose as little information about the system as possible. On the other hand, we should also like to make the model as simple as possible to lend itself to convenient mathematical analysis, so that the person who uses this model for analysis and synthesis will retain his sanity in a sense, because if it is going to be a huge a complex type of model, he will never be able to solve it. Therefore these are the two conflicting requirements in the evolution of a model of a given physical system. On one hand, it should be as complex as possible so that it will lose as little information about the system as possible. At the same time, it has got to be simple enough to lend itself to convenient mathematical analysis. Now we very often refer to the model itself as a system, even though we must always keep at the back of our mind that the model is a mathematical representation, is an idealized representation. The actual physical system is something different, and in some ways the physical system may not, the characteristics may not agree with the model, and if it is so, then we have to refine the model to make it more realistic wherever it is warranted. Now in arriving at a model for a particular system, the derivation of the model is specific to the particular discipline. You must study the physics of the situation, you must know the characteristics of this and arrive at a suitable model. But once we have evolved a model, then a whole lot of the systems can be analyzed through a common framework, a common set of mathematical tools which can be used to analyze a whole lot of these different system models, because the mathematical equations that govern the operation of these various systems are more or less the same. Therefore there is a unifying body of techniques and knowledge which come under the general title system theory or principles of system analysis, which will be the main scope of our study in under this course. Then after having discussed what a system means and what a model means and how these analysis of these various models are facilitated by a common body of tools coming under the name system analysis, system theory. Let us now see how we represent a system. Very often we are interested in finding out the response of a system under the influence of a particular input. We are not so much bothered about the various variables, the various signals internal to the system. In this event, we represent a system as a black box. And the various inputs that are given to the system are represented in this manner, maybe call this x1, x2 right up to xm. And under the influence of these various inputs, there are certain responses in the system which we are interested in. These are called the outputs or responses. Similarly, the inputs are called excitations also. Other name is excitations. So we may say the system responds under the influence of an excitation, or the system gives an output under the influence of an input. And there may be n such responses we are interested in. So in this particular system, we possibly have m inputs and n outputs, and then a representation like this is referred to as a multiple input, multiple output, multiple input, multiple output system. So let us consider an electrical network. And you have several sources, voltages and currents, and we would like, these are the various inputs to the electrical network, current source and voltage sources. We are interested in finding out the voltage and currents at different points. We are interested in finding out all those responses, so we can model this as a multiple input, multiple output system. On the other hand, very often we might be interested in finding out the influence of one particular input, and we would like to find out the response at a particular location. Then we have x of t may be the input signal, y of t is the output signal. So we may call this again as input or excitation. And this can be called the response, output, and this will be called single input, single output system. For the class of systems which we will talk about later, linear time invariant systems, if we have a complete knowledge of how a system behaves with a single input and a single output and a particular output, then we can use that information to get a particular response when a variety of inputs simultaneously occur by the principle of superposition, and this is something which we can always do for the particular class of systems that we are talking about. So our concentration may be for most of the time on a single input, single output system, but that does not in any case take away from the generality of the tools that we employ. to simplify this notation, this is a block diagram representation of a system. I mentioned this as a black box because we are not particularly interested in what is inside. Therefore, we can assume this. We have two terminals where the input is fed and two terminals where its output is fed, taking the electrical circuit as an example. And this whole concept of a particular input giving rise to an output can also be very succinctly and compactly indicated as xt and ROYT. That means in a particular system, once we know what the system is, we can say then the system input xt gives rise to an output yt. This is the excitation, this is the response. So very often we use this type of notation when we have to deal with a particular system and we would like to have a variety of inputs, and what are the outputs that you get, we use this kind of compact representation to indicate the input output relations of a system. As I said, systems are quite diverse in nature, and naturally their properties also will be diverse in nature, but we would like to classify the systems depending upon the particular property or characteristic that we have in mind. So let us now talk about classification of systems. One can classify system as either a static system or a dynamic system. A static system is one in which the output depends upon the input at that time and on nothing else. It does not depend upon what happened in the past. The past history of the system is immaterial. So if you give a particular input, the output is dictated by that input. Nothing else is required. Take for example an electrical resistor. The current in that resistor depends only on the voltage at that particular point of time. Not that how that voltage has come about, nor about its rate of change, etc., but it depends just on the voltage at a particular time dictates the current in that resistor. So if a resistive network is there, a one port resistive network, then if the input voltage is given, the current is immediately deduced by the magnitude of the voltage at that particular point of time. So static networks are also sometimes called memoryless networks or memoryless systems. Example, a resistive network. Whereas a dynamic network, it is not enough if you know the values of the instantaneous values of the inputs at that time. You should know something more. You should know perhaps a kind of summary of what happened in the past in the form of, suppose let us take an RLC network for example. If you want to know the response of an RLC network to an impressed excitation, the driving force, you should also know what is the initial charge in the capacitor, what is the initial current in the inductor, and this is what has come about because the past history of the network, whatever excitations it has been applied with and whatever remnants it has left in the system. So in a dynamic system, the response depends not only on the instantaneous values of the input, but perhaps on the derivatives of the input and also the integrals of the input quantities and so on. So it does not merely depend upon the instantaneous values, the rate of change of the inputs, the integrals values of the inputs, the past history of the input as summarized by the initial conditions are all important in the case of dynamic systems. Example, an RLC network. So if you are having an RLC network with given excitation functions, It is not enough to know the complete solution problem, you should also know the initial currents in the inductors and the initial charges in the capacitors. So it turns out that when you want to describe a static system, the equations governing the performance turns out to be purely algebraic in character. Whereas since in a dynamic situation you need to take stock of the derivatives, the time variation of the various quantities, we have integral differential equations, or an integral differential equation can always be reduced to a differential equation, but in general we can say integral differential equation. So you have on one hand some differential equations, and also you have differential derivatives as well as integrations of the integrals of the various quantities, and so in general it will be an integral differential equations that govern the performance of a dynamic system. A second method of classification of systems is to categorize them as a continuous time system or a discrete time system. Alternately discrete time. In a continuous time system, the input output relations are defined for every instant of time on a continuous basis. In other words, we are interested, or we can calculate in principle, the variables at every single point of time on the time axis on a continuous basis. Whereas in a discrete time system you have these input output relations. Discrete time system, you would have an input output relation defined at particular discrete points along the time axis, not necessarily at every point of time. We will see the meaning of this in a more clear fashion as we go along. So let us talk about a continuous time system. An example of a continuous time system, as an example let us take this RC network. So we have a source Vs, a voltage source, we have a resistance and a capacitance, and this is the voltage across the capacitor Vc. So we would like to view this as a system in which Vs is the input quantity and the voltage across the capacitor V0 or Vc as the output quantity. So the input output relation in this case is defined by the following relation. After all, Vs equals Vc plus the voltage across the resistance, and the voltage across the resistance is R times the current to the resistance I, and the current in the resistance is C dVc dt. So R times C dVc dt is the voltage Vs. So if Vc is the output and Vs is the input, there is this differential equation governing the input quantity with the output quantity. So you can put this in a compact fashion as d plus 1 over Rc times Vc equals Vs over Rc, where d is the derivative operator. You can, instead of dVc by dt, you can write just dVc as a more compact notation, which I am sure you are familiar with this notation. D dividing this entire all the terms by Rc, this is what you get, d plus 1 over Rc Vc equals Vs over Rc. So this is a first order differential equation, and this is the input output relation for this. So this is, you can solve for this depending upon the Vs that you are having, and you can get values of Vc at every instant of time, and the equation itself is defined for every instant of time. This is an example of a continuous time system. As a discrete time system, you have these input output relations described for discrete values along the time axis. So if this is the time axis, you might be having equations which are valid only at certain points. So the time axis may be defined in units of seconds, microseconds, months, years, as the case may be. For example, I may take this t in years, in which case suppose I graduate this 1, 2, 3, 4, etc. Say this is, break this up, say n, n plus 1, etc. I am interested. I will have an equation which describes the operation of the system at particular points on the time axis. Not, we don't care what happens in between 2 and 3. So that is called discrete time system. As an example, let us consider an organization in which yn is the number of persons in the organization in an establishment, number of persons in an establishment at the beginning of the nth year, at the beginning of the nth year. That is yn. Let me take xn as a number of persons who leave the organization in the nth year, who left the organization, either they retired or left for other jobs or died, whatever the reason might be. Xn is the number of persons who leave the organization in the nth year. Let Wn be the number of persons recruited, new recruits in the nth year. Then you can clearly see that given these variables which describe the operation of the system now we are concerned, the variables are these, we are interested in the number of people employed in the organization. Y of n is the number of persons at the beginning of the nth year. These are the number of persons at the beginning of the previous year. And out of these, x people, xn minus 1 persons have left the organization during that year. Therefore, so many must be less by that amount. But so many people might have been recruited. Therefore, plus wn plus n minus 1. This is the equation which gives us the number of persons in the organization at the beginning of the nth year in terms of yn minus 1, xn minus 1 and wn minus 1. Let me further assume that the recruitment policy of the organization is such that at the beginning of each year they would like to find the vacancies. Their sanction strength, let us say, is 1000. Therefore, 1000 minus yn is the number of vacancies at the beginning of the nth year. And then they put out an advertisement, recruit people, and then the recruitment policy is such that it takes about a year to recruit people, and therefore whatever recruitment steps have been taken in the nth year will take effect only in the next year. So the number of people recruited in the n plus 1th year is, let us say, this is the target, but all the people who have been recruited may not join, or maybe there may not be suitable candidates. So let us say 80% of this target amount is recruited. So wn plus 1 is 0.8 times 1000 minus yn. So if you substitute now this expression into this, you can now write yn equals yn minus 1 minus xn minus 1 plus 0.8 times wn plus 1 is this. So wn minus 1 is 0.8 times 1000 minus yn minus 1, n minus 2, because wn minus 1, this index now is n plus 1 has gone down by 2 steps, therefore this must also go down by 2 steps. That means the persons recruited in the n minus 1th year will be based upon the number of people in position at the beginning of n minus 2 second year. So if you substitute all this, you have now an equation which will be, the previous equation then leads to yn minus yn minus 1 plus 0.8 yn minus 2 equals minus of x n minus 1 plus 800. So this is an equation which will enable us to calculate the number of persons in the organization at any year n in terms of the values of yn in the previous years, previous 2 years, and also the number of people leaving the organization in the n minus 1th year. So this can be thought of as a discrete time system in which you have the input xn, the number of people leaving the organization, that is something which is unpredictable, that is the kind of input that you have for the system. So under the influence of the input, we would like to calculate the output, or the resultant is the number of people in the organization in the nth year, yn. So it can be represented by means of a discrete time system which has got xn as the input and yn as the output. Now we have to keep in mind that these two quantities, the input and the output xn and yn, have meanings only for integral values of n. So n is the number of years in our case, 0, 1, 2, 3, and so on and so forth. We can't read any meaning in that for non-integral values of n. This has meaning only for n equals 1, 2, 3, 4, and so on. The distance between successive units in our case happens to be years, but in general it could be seconds, minutes, or whatever you are having. It is always also conventional that in most of the cases we take these intervals at regular points along the time axis. So it could be seconds, it could be months, it could be days, it could be years, and so on. In our case it happens to be years. So the point to observe is this is valid only for discrete values of n. And usually they are integral values of n in the appropriate set of units. Now secondly, this kind of equation is called a difference equation. In contrast to the differential equation that we come across in continuous time systems. In discrete time systems, the equation will be the independent variable takes on discrete values, and the equation of this type is called the difference equation, in contrast to differential equation that we come across for continuous time systems. So that is the major difference between a continuous time system and a discrete time system. In a continuous time system you have a differential equation coming into operation. In the discrete time system you have a difference equation that is important. Secondly, what we would like to know is the order of this difference equation. It is the difference between the highest index and the lowest index. So n and n minus 2, this is the dependent variable, the difference between these two is 2. So in our case this is the second order difference equation. In this case, it could be higher orders in a general case. So in the discrete time system, the points to note are that the equation is valid for specific integral values of the independent variable m, and the independent variable usually is time, that is why this is called discrete time system. But the same methodology is applicable even to situations where the time may not be the independent variable. For example, if you have got along a line, you would like to point out, you would like to graduate this, and you would like to have an equation which specifies the values of some kind of independent variable along discrete points along the line. The space coordinate can also be an independent variable. Even those systems are referred to as discrete time systems because this is a more common type of system. We can say discrete system, but we call it discrete time system even in that case. So the two important differences between a continuous time system and discrete time system are continuous time systems, the differential equation is comes into play. Here the difference equation comes into play, and the continuous time system, the variables are described at every point in time along the continuous basis. In the discrete time system, they are defined only for discrete values of the independent variable, which is usually time, and that is why it is called a discrete time system. A third important classification is the concept of linear system and nonlinear system. In a linear system, if an input x1 of t, I am talking about a continuous time system now. This is our discussion will be mostly in terms of continuous time systems. At a later point in time of time in this course, we will talk about discrete time systems in specially, but wherever examples are given, we talk in terms of continuous time systems now for the most part. If x1 of t gives rise to an output y1 of t and x2 of t gives rise to an output y2 of t, then for a linear system, no matter what x1 and x2 are, a constant times x1 of t plus another constant times x2 of t will give rise to an output which is c1 y1 of t plus c2 y2 of t for all constants. C1 and C2. This is what is referred to as the principle of superposition. Sometimes people refer to this, break this up into two parts, homogeneity and additivity. What they say is if x1 of t gives rise to y1 of t, then c1 x1 of t gives rise to c1 y1 of t. That is called the principle of homogeneity. Then the second part is if x1 of t gives rise to y1 of t and x2 of t gives rise to y2 of t, then x1 plus x2 will give rise to y1 plus y2. That is called additivity. But now we will combine these two together and we will say c1 x1 of t plus c2 x2 of t will give rise to c1 y1 of t plus c2 y2 of t for all constants c1 and c2. And this is the class of systems which are called linear systems, one which obeys this principle of superposition. And most of the electrical networks that we have solved earlier belong to this class. But you must keep in mind that this particular superposition principle will be valid, for example, in the case of electrical circuit with zero initial stored energy. If a capacitor has got some stored energy in that, this principle of superposition will not be valid. Let us take an example. For example, I will say this is applicable to linear networks as a special case, of course, with no independent sources or stored energy. Important. For example, this is a linear network resistance. Suppose I have a source here, 2 volts, 1 ohm. Then if I have an input here Vi, and I will take the current to be my response quantity, I equals Vi minus 2 divided by 1 or Vi minus 2. And if I have two different voltages V1 and V2, and find the currents I1 and I2, and if I say if I have V1 plus V2, then I will not get I1 plus I2. As you can see, for example, I1 here is Vi1 minus 2 for one particular excitation. For a second excitation I2 equals, it is Vi2 minus 2. But suppose I have a single excitation which is equal to Vi1 plus V2, then the current would be Vi1 plus Vi2 minus 2. That will be the current when I have a single excitation Vi1 plus Vi2. But I3 is not equal to I1 plus I2. Why? Because of the source here. I3 is not equal to I1 plus I2. So when you apply this linearity principle or superposition principle, you must make sure that you are applying it to a network which does not have sources or stored energy for that matter. Let us take a second example to illustrate this second point which I have in mind. Suppose I have a capacitor which has got an initial stored Vc, this is C, and I have a current source as excitation. So I will think of this as a system with Is as the input quantity and Vc as the output quantity. Okay, and let me assume that Vc0 equals some rho volts. That is, the initial capacitor voltage is so many volts. Then you have the relation Is equals Vc equals 1 over C 0 to t Is dt. That is the additional charge that is conveyed to the capacitor in the interval from 0 to t. This is Vc of t, plus the initial voltage that is across the capacitor rho. That means this initial voltage plus the increment in the voltage due to the additional charge that has been conducted to the capacitor in the interval 0 to t. This is the equation between the input quantity Is and the output Vct. Now let us take a situation where I have Is is, there is one Is1, then you will get Vc1 equals 1 over C integral Is1 dt plus rho, 0 to t of course. And let us take a second excitation which is 0 to t Is2 dt plus rho, that is Vc2. So Is1 and Is2 respectively will give rise to these voltages Vc1 and Vc2. Suppose I had a single source which is Is1 plus Is2, both of them are acting in parallel simultaneously. Is1 and Is2 together charging the capacitor. Then the third time the voltage Vc3 will be 1 over C integral Is1 plus Is2 dt plus rho, again because initially the capacitor is charged to rho volts. Now you can see Vc1 plus Vc2, which are the responses due to Is1 and Is2, will not add up because Vc3 is not equal to Vs1 plus Vc2. What spoils is this initial charge in the capacitor, because when you add these two up you get 2 rho, but it is only 1 rho, which means that the argument is that this principle of superposition is valid only for systems which are purely linear, in the sense that they should not have any sources inside, independent sources, or initial charges on the capacitors or initial currents in the inductors which are always considered to be equivalent to sources. So this is an important principle, and to keep in mind when you talk about linearity of systems. A system which is not linear is of course called nonlinear. The difference between the linear system and a nonlinear system is, a linear system is governed by linear differential equations. And a nonlinear system by nonlinear differential equations. What is the meaning of a linear differential equation? Linear differential equation is one in which the coefficients of the various derivative terms, coefficients are not functions of the dependent variable. I will take some examples later on. So if I have a term like d squared by dt squared, its coefficient should be either constant, it could be a function of time, but it can't be a function of another derivative of y or y itself. So linear differential equations are the one which govern the operation of a linear system, and if the equation fails to be linear, then it becomes nonlinear, and that the superposition principle will no longer be valid. We will take up some examples of these equations which govern the performance of the different kinds of systems in the next lecture, but let me stop at this time and briefly summarize what has been discussed so far. Starting with the scope of the course, which is mainly the dynamic performance of linear time invariant systems and networks, we had a look at the reference and textbooks that you may use for following this course. Then I mentioned the background material I assume that you have had before taking up this course. Then we looked at the meaning of a system. Broadly speaking, we said system is a collection of objects or system components united through some form of interdependence among the various constituent components. We said a network is a special kind of system in which all the variables will be of a particular kind, or one kind. An electrical network, a mechanical network, given as examples. And then we also talked about the modeling of a system. Modeling of a system is done in the form of ideal components put together to constitute the system, interconnected in some fashion. And we do this idealization keeping in mind on one hand that the complexity of the system should be not too large to vitiate convenient handling of the model. At the same time, it should be sufficiently realistic so that the results obtained from the model are generally realistic in practice, otherwise the model has to be refined once again. Also mentioned that the model and system, we use the two terms interchangeably, almost as if the model itself is a real system, which is of course not true. Then we looked at the representation of a system, and we talked about the multiple input multiple output system and single input single output system. And then we went on to discuss the various kinds of classifications of systems, because as I mentioned, we are talking about linear time invariant systems, therefore we must know what they mean. So with that in mind, we looked up at we are trying to find out the classification of the important classifications of systems. We talked about the difference between static systems and dynamic systems. We talked about the difference between continuous time systems and discrete time systems. And lastly, we have talked about the difference between linear systems and nonlinear systems. The discussion on the linear and nonlinear systems is not complete, because I would like to give some examples of the governing differential equations for both the types of systems, and we'll pick up at this point in the next lecture and continue our discussion from that point onwards.